Welcome to the Trong BK Engineering channel. Let's jump right into this explainer. Have you ever stared at a super complex CAD model on your screen and just thought, okay, how in the world does this digital dream actually become a physical reality? Well, if you have, you are exactly in the right place. Today, we're diving into the Mechanical Practicum, specifically course ME 3150. Think of this as your essential guide to bridging textbook theory with the hands-on and, let's be honest, sometimes pretty gritty reality of the manufacturing floor.
Here is our visual syllabus for today. We'll be crossing that bridge from theory to practice by hitting on workshop safety, essential machinery, cutting tools, precision measurement, and finally the complete industrial workflow. Let's get right into it.
Section 1. The Engineering Bridge. Let's start by digging into the core philosophy of the ME 3150 course.
It all starts with one really fundamental question. How does a random piece of raw material become a highly precise mechanical component? I mean, a beautifully optimized design on paper, or, a computer screen, that alone can't build a working machine. To be a truly great engineer, you really have to understand how raw materials, heavy machinery, cutting physics, and manufacturing workflows actually interact out there in the real physical world.
So, the crucial point boils down to this equation you see right here. On one side, we've got engineering theory. That's your physics, your advanced math, your CAD design. And on the flip side, we have practical engineering skills. That means actual machining, the physical assembly, and real-world maintenance. It's simple. Theory plus practice equals true engineering mastery. One literally cannot exist without the other on the factory floor.
Section 2. Workshop safety. Because before we even think about touching raw materials or spinning a chuck, we absolutely have to talk about safety.
Now, this might actually be a surprising fact to beginners, but wearing gloves while operating spinning machinery is strictly forbidden. Seriously, no way. Gloves can super easily get caught in a rotating spindle, and they will pull your hands right in with them. You only use gloves when you're safely handling heavy or bulky raw materials far away from those moving parts. Other absolutely critical rules for the practicum include never leaving your assigned station without permission, reporting any accidents immediately, don't hesitate, and taking the responsibility to thoroughly clean your machine right after you're done operating it.
Moving on to Section 3, Essential Machine Tools. With our safety protocols completely locked down, let's talk about the real stars of the workshop.
Take a look at this classic 1A 1616 engine lathe. This thing is the absolute workhorse of turning operations. Just notice its heavy structure, right? You've got the headstock on the left housing the gearbox, the carriage right in the middle holding the tool, and the tailstock over on the right. This machine operates on a very specific, cool principle. The raw workpiece is clamped in, it spins at a really high speed, and the cutting tool just moves linearly to literally peel away the material.
And this brilliantly illustrates that physics of cutting we were just talking about. On the left, you can see the basic lathe turning process. So the blue workpiece spins at a specific RPM, and the cutting tool feeds into it. But contrast that on the right with the complex kinematics of other machining operations. You can see milling, where the tool itself is actually what rotates, or gear shaping, where both the tool and the workpiece are moving together in this perfectly synchronized dance. So while the lathe handles cylindrical parts, you have to remember a full workshop is like an ecosystem. Milling machines use rotating cutters to carve out flat surfaces and complex pockets. Drilling machines, as you'd guess, handle precise hole production. And when you need an incredibly precise, mirror-like finish, say you're working on aerospace components, you're going to move over to grinding machines. Finally, CNC machines take all these concepts and add computer-controlled automation for just unmatched, repeatable precision.
Section 4. Cutting Tools. Let's zoom in even further to the exact point where metal meets metal.
Because as you can see, different cuts require very specific tool geometry. This whole arsenal of milling cutters ranges from cylindrical cutters and end mills at the top, all the way down to dovetail cutters for very specific interlocking joints, T-slot cutters, and intricate profile cutters. Every single geometry here is engineered to do something vital: evacuate metal chips safely while leaving an absolutely perfect surface behind.
Just notice the distinct difference between these two tools. Over on the left, we've got a solid end mill, carved from a single piece of really hard material, which is absolutely perfect for detailed contouring and pocketing. But on the right, that's a massive indexable face mill. Instead of being one solid chunk, it actually holds small replaceable carbide inserts all along its edge. It's designed for aggressive, high-speed material removal across wide, flat surfaces. It's a real powerhouse.
So, to synthesize this entire section, the machining process is simply the controlled removal of material.
Think about it like this. We rigorously lock down the workpiece, restricting all 6 of its degrees of spatial freedom, and then we use a hardened cutting tool with highly calculated cutting and feed motions to shear away the excess material. Honestly, it's basically industrial sculpting driven by physics.
Section 5. Measurement and assembly. So the cutting stops, the machine powers down. What happens next?
Well, how do we actually know if we made the part correctly? This brings us to a vital truth of the Mechanical Practicum. Manufacturing is never complete without precision measurement and inspection. We rely heavily on highly accurate instruments like vernier calipers, micrometers, and dial indicators. These tools guarantee that the physical part sitting in our hands actually matches the crazy microtolerances dictated by the original CAD model. Without measurement, you're literally just guessing.
Section 6. The industrial workflow. Let's step back and see how all of this builds into the big picture.
This sequence perfectly charts your progression through the practicum. Because, you don't just walk in and start building engines on day 1. You start at step 1, carefully identifying the machines and tools. Then, step 2 is hands-on machining practice. By step 3, you're bringing those components together for assembly and rigorous inspection. Step 4 introduces repair and maintenance, so fixing what's broken. And it all culminates in step 5, understanding and organizing the actual processes for true industrial production.
But here's the thing, the practicum isn't just about bending metal, it also develops some absolutely vital soft skills. You'll be practicing teamwork, creating technical presentations, and honing practical engineering communication. Why? Because in a modern industrial environment, complex mechanical systems are never built by just one person sitting in a vacuum. They're brought to life by teams of professionals who know exactly how to communicate their technical ideas clearly and effectively.
I want to leave you with this final, genuinely empowering thought, straight from the core of the course material. A great engineer doesn't just design on paper, they master the physical realities of the manufacturing floor. I really hope this explainer has given you a clear roadmap of the Mechanical Practicum, and maybe even sparked your curiosity to get your hands safely dirty. The theory is in your head, the tools are waiting in the workshop, so the only question left is, what will you build?